Okay, so say yes. Yes. Okay, so welcome to the second lecture on indirect detection by Tracy Slatyer.
Okay, good morning, everyone. Thank you all for being here, especially at 9 a.m. on such a gorgeous morning. So I want to continue today our discussion of indirect detection from yesterday. So yesterday, we talked about various parametric estimates for how much energy transfer, annihilation, or decay could induce from the dark matter to the visible matter. And we talked about the possible detectability of those signals through cosmic time. But we haven't yet talked about the main way that indirect detection is actually done, which is that rather than looking at changes to the history of the universe, we just look for the particles from indirect detection directly. So we look for the particles that are produced by annihilation. When you're doing that kind of search, you don't care just about the total energy injected, you care about the spectrum of the particles, and you care about the direction that they're coming from. So in the second part of this lecture, I want to tackle the first of those questions, think about what kind of particle energy spectra we can get from annihilation and decays, how that's going to change our signal sensitivity, and how we can work out how the energy spectra of those particles change between when they're first injected by annihilation and decay and when we actually see them in our telescopes. And I want to do an example of that for charged particles. But before we get to that, I want to begin by just continuing the discussion last time, just thinking about sort of how much energy is injected from indirect detection, and using those insights to think about scenarios where indirect detection signals are either going to be very suppressed from what we talked about last time or enhanced from what we talked about last time. So at the end of this lecture, ideally, you'll have sort of a good overview idea of models where indirect detection signals are either going to be really easy to see or really hard to see, an understanding of the possible energy spectra of particles that we can see in our telescopes from dark matter annihilation and decay, and if time permits, at the end, how, as charged particles propagate through our galaxy, they lose energy, and that affects the spectra of charged particles that we can see in our detectors. Okay, so that's the goal for today. So let's begin by talking about, what are the dream and nightmare signals for indirect detection. So we talked last time about the plausibility of seeing dark matter decaying with a lifetime of up to 8 to 10 orders of magnitude longer than the age of the universe, and thermal relic dark matter with mass scale, and being able to test the thermal relic scenario for mass scales up sort of 10 to 100 GeV. But not all models have visible indirect detection signals like that, and there can be significant model-dependent modifications to the basic picture that we laid out last time. So, what are the dream and nightmare scenarios for ID? So I'm going to focus here mostly again on cases where there is some kind of thermal freeze out in the early universe, just because this is a convenient benchmark. But these basic principles of which models make it really hard to see an indirect detection signal and which models do not are going to be more general. So let's first talk about the case where annihilation is suppressed at late times. This may be relevant to you. For example, we said last time that based on these estimates of limits from the Lyman alpha forest and from the cosmic microwave background, it's hard to have thermal relic dark matter that annihilates in the way we described last time with a mass scale lighter than about 10 GeV. But we have a whole lecture series here by Tong-An Lin on sub-GeV dark matter. And you will see when we talk about accelerator searches to dark matter and direct searches to dark matter that very often there are lines in this plot saying thermal relic target line. So you might say, well, why is this the case if we've already said that you can't have thermal relic dark matter below 10 GeV? Well, the answer, of course, is that just because the dark matter was a thermal relic in the early universe, that doesn't necessarily mean that its annihilation is still unsuppressed today. So there are various mechanisms that can decouple the annihilation rate in the early universe, which is relevant for production, and the annihilation rate in the late universe, which is relevant for indirect detection. So let's just go through some of those possibilities. So one possibility is that the annihilation is not just dark matter, but it's dark matter against some other particle, and that other particle isn't present in the late universe. So GM needs a partner to annihilate plus the partner abundance is suppressed at late times. So the very simplest version of that, sorry, question one?
Oh, thanks. Can that partner be in the dark sector?
Yeah, absolutely. Yeah. So I'm trying to make this fairly general, but the very simplest example of this is that you have asymmetric dark matter. So there's dark matter, there's anti-dark matter, they have slightly different abundances. The anti-dark matter all annihilates away in the early universe, and it's that that sets the abundance, not just the annihilation cross-section. Then at late times, there'll be very little anti-dark matter left. So the simplest version of this, well, by some metric of simpleness, is asymmetric DM annihilations DM plus anti-DM goes to the standard model. So this does require the annihilation rate to be large enough to annihilate away all the anti-dark matter in the early universe. So you actually need larger than the standard thermal relic cross-section in order for the abundance of the anti-dark matter to be the limiting factor. So I guess that's not the rate. The cross-section should be larger than the standard thermal relic cross-section. All anti-DM gets depleted early on. So I don't know if you guys did the calculation for asymmetric dark matter last week, but it's a reasonably straightforward calculation. But what you find is because the anti-dark matter is annihilating against the dark matter component, which is much more abundant than the anti-dark matter, it annihilates really efficiently, and its abundance actually gets depleted in a way that is exponentially sensitive to the annihilation cross-section, not just linearly sensitive. So in that case, the amount of anti-dark matter can be very small in the late universe. There are some models where even though you have asymmetric dark matter, you still get a big signal at late times. That can be due to other enhancements to annihilation, or it can be because there's some mechanism that regenerates the anti-dark matter component at late times. If that happens, you tend to get quite a big signal because you needed a large annihilation cross-section to deplete the anti-dark matter in the first place. But bog standard anti-dark matter, asymmetric dark matter model, if you can deplete almost all the anti-dark matter in the early universe, then you don't need to worry very much about indirect detection signals at late times. So that's the sort of V1 of this. But it doesn't have to, but this general mechanism that you need some other part, the dark matter needs some other particle to annihilate, and if that particle goes away at late times, it can't annihilate, it's not restricted to the case of asymmetric dark matter. Another case that's very popular when thinking about light dark matter models is you can have a situation where dark matter is what's called a pseudo-Dirac fermion. So I'm just going to kind of sketch the particle physics here, but if people want to know about it in more depth, then they can come, then you should feel free to ask questions or come talk to me later. So the idea here basically is let's start with a model where the dark matter, where at high energies, the dark matter is a Dirac fermion charged under some dark Q1 gauge group, okay? So a Dirac fermion has 4 degrees of freedom, and it has an interaction with my dark, with the gauge boson of my dark Q1 gauge group, which I'll call the A prime. That just looks like this. Okay, so it's just like an electron-proton interaction, but in the dark sector. But then it's possible to add extra terms to the Lagrangian that split the 4 degrees of freedom of this Dirac fermion into 2 Majorana fermions that are slightly different in mass. Okay, and that's what's called a pseudo-Dirac fermion. So at low energies, there are 2 slightly different mass eigenstates which each have 2 degrees of freedom. Okay, this is a sketch of the particle physics. The important thing is at the end, there's a dark matter Majorana fermion, and there's a slightly heavier, like dark matter star Majorana fermion. So we'll call these two fermions chi1 and chi2, and we'll say they have masses m1 and m2, which are close but not identical. So they, like, the extra operator you're adding is basically giving a small Majorana mass to this Dirac fermion. So in this case, so now we have our spectrum of our dark sector, which is chi1 and chi2 slightly heavier. And this is a setup for the kind of inelastic dark matter models that Jody talked briefly about yesterday. Like that's one thing that you can do with this kind of model. But the other thing that you can notice with this kind of model is Majorana fermions can't carry conserved charge, which means that there is no, that if you ask, okay, what does that vertex translate to in this new model? There is no vertex that looks like this. That is not allowed because the Majorana fermion doesn't carry conserved charge. What this vertex does transform into in this new base of Majorana fermions is a vertex that looks like this. Okay, so this vertex, like you can do it explicitly, you can work out the calculation explicitly, and you find that this vertex goes to 0. The dark one charge. Okay, so if you know that this is, so now this is the only vertex available, and this is the question.
Maybe I missed it, but why are we saying they're newly degenerate?
You don't have to make them nearly degenerate for what I've said so far. When people say pseudo Dirac, they usually mean the case where it's close to Dirac, and so they're pretty close in mass.
Okay,
but,
and we call it inelastic when they're farther apart.
So if you want to do inelastic scattering in direct detection, you want them to be pretty close in mass because the dark matter only kinetic energy is only about 10 to the minus 6 of the mass of the dark matter in our galaxy, because the dark matter is going at about 10 to the minus 3 C if it's bound to our galaxy. So its kinetic energy is the square of that, so 10 to the minus 6 times the mass of the dark matter. So if you want to be able to so the inelastic dark matter scattering would be like this. A chi1 comes in the lower state, it exchanges an A prime with standard model particles. So to do this, you have to assume that there's some, so let's add this extra ingredient. Let's have our A prime has some mixing, we'll call it epsilon, with the standard model photon, okay? So then there's an interaction with the standard model that looks like this. But in order for this process to be kinematically allowed, you need the mass splitting between chi1 and chi2 to be smaller than the kinetic energy of the incoming dark matter particle. So it has enough energy to sort of excite into this higher state. So that means the mass splitting needs to be smaller than 10 to the minus 6 times the mass of the dark matter. So if you want to use it for direct detection, you need this mass splitting to be pretty small. You don't need to use it for direct detection. You can use this to just turn off the direct detection signal if the mass splitting is too large.
Sure.
Is
Question there?
energy at which the Dirac fermion is splitting into the Majorana fermions, is that before or after freeze out?
So it depends on how you set up. So the question was, does this splitting, I said this splitting happens at low energy, the integral of the Dirac fermion to Majorana fermions, does it happen before or after freeze out? It depends how you set up the term in the Lagrangian. I mean, one way that I'm familiar with, you can add so in general, so the way that I'm familiar with it, to do this, you usually have to break the dark U1 in order to allow for this term. It's when the dark so you can set this up in multiple ways, that the breaking of the dark U1 symmetry is what allows for this splitting. And so that means that you're only going to get this splitting after the dark U1 is broken. And so that can happen at various times. But again, if you choose your parameters such that this splitting is really small, then even if these things technically have different masses in the early universe, if the mass splitting is much tinier than the temperature, then it won't really matter for the temperature during freeze out, then it won't really matter for the freeze out calculation. These two states will be equally populated during freeze out. It will be very easy to transition back and forward between them during freeze out because they're essentially degenerate in mass compared to their kinetic energy. And so it's only once the kinetic energy of the particles drops below the mass splitting. So yeah, I guess that's the other reason to assume the mass splitting to be small, as it makes your freeze out, but you can just use the freeze out cosmology for Dirac dark matter and assume that they're degenerate, but then say, oh, at late times, once their kinetic energy is small compared to this mass splitting, then we won't be able to excite the heavier state, and then they'll behave differently. So as I said, let's assume the A prime mixes with the standard model U1. That means it couples to the gamma and Z with some mixing epsilon. So then if we ask, okay, what is the diagram that allows this, what is the diagram that allows these dark matter particles to annihilate into standard model particles? What does that look like? It looks like this. So this could be a gamma or a Z, and then this is going to be a standard model particle and its antiparticle, okay? So if the A prime is sufficiently light, there will be other annihilation channels, but if the A prime is heavy enough that you can only make it off shell, then this is what you would think is the dominant annihilation channel. And yeah, let me just, yes, this is the dark age boson. Okay, so in this case, in the Dirac case, this would be like a chi-chi bar annihilation into standard model particles. Having split them, it's a chi-1, chi-2 annihilation. But then once the temperature of the universe drops below M2 minus M1, then the abundance of M2 will start to go down. It will be Boltzmann suppressed. The abundance of chi-2 will be Boltzmann suppressed, will go down. Another way to say it is the chi-2 can decay away down to the chi-1. So in the early universe, there are plenty of chi-2s around, and it's easy for this annihilation to happen. But at late times, the abundance of chi-2s will be smaller while they stay in equilibrium, just because it's Boltzmann suppressed. And at sufficiently late times, the chi-2 may also just be able to decay down to the chi-1, and so the abundance of chi-2s will be small. It's a question.
Okay, thanks. Is it possible that instead of annihilating into standard model, standard model baryons, there's just going to be an injection of energy into the photon bath?
Yeah, okay, so the question is like, could I have it? The question was, is it possible that instead of going into like standard model baryons, or I guess or electrons or positrons or other charged particles, could there just be an injection of energy into the photon bath? Yes, so the answer is yes, you can have that happen. Dark matter had better not couple very directly to photons, or it wouldn't be dark. Although I mean you can, but you can have light dark matter where it's dominant annihilations or dominant decays or into photons or neutrinos. Usually that happens because the dark matter is too light to decay or annihilate into anything heavier. And so then if you modify the photon bath, then photons can photoionize, photons can heat the baryons. So there you can get the kinds of signals that we talked about earlier. And in the present day universe, you can look for the photons directly. If you manage to annihilate or decay primarily into neutrinos, then it's much harder to see. But again, you can try to look for the neutrinos directly today. Question off the back.
Operators which are added to the Lagrange, what kind of dimensions is that?
So there are a few different ways. Okay, yeah, sorry, yeah, thanks, Marco. Yeah, so the question was when you add these operators to the Lagrangian to give a Majorana mass to the chi-1 and chi-2, then what kind of dimension can do these have? I'm going to mostly defer this question to later. I can point you to some references, but there are multiple ways to do it. I mean, there's one way is to add it. So in most of these theories with dark sectors, you can also have a dark Higgs in the theory. So if the dark Higgs has the correct charge, you can do it just with the Yukawa interaction to the dark Higgs with the small Yukawas. That's STIM4. You can also do it by adding a dimension. You can also do it by adding a dimension 5 term. So yeah, but I can point you to some references with various ways. There are multiple ways to construct this extra Majorana term.
On Zoom,
yeah.
Is there a possibility of bound states formation?
Yeah, but okay, so question on Zoom is there a possibility of bound state formation? Yes, if either the coupling in the dark sector is heavy enough or this A prime gauge boson is light enough. Both have, so in that case, you might have a situation where, so you could have situations where there are other annihilation channels besides this one that are important, like maybe two chi-1 particles conform into a bound state, and that that bound state can subsequently undergo some kinds of scattering annihilations that allow that to serve as an annihilation channel. So yeah, so that can modify this basic picture. In general, if the reason you're forming a bound state is because the A prime is really light, then that can open up, it's like is much lighter than the chi's, then that can open up a channel that looks like this, followed by the subsequent decay of the A prime into standard model particles. And so like that, then this is a possibility if A prime is light. So in that case, you will still get a strong constraint from direct detection because this process is not suppressed at late times. The chi1s will just happily annihilate away into A primes through the whole age of the universe. The A primes will promptly decay. In that case, if the A primes are really light, you can all. So this will actually be one of the enhanced annihilation scenarios that we talk about in a moment, that exchanges of the A prime before the annihilation can give an attractive force between the particles, which greatly enhances the annihilation. So this tends to be a case where, yes, it can absolutely happen. If it happens, it's great for indirect detection. You get a huge signal, and thus these models are pretty easy to constrain.
Do you necessarily need the the mixed coupling, or like you can just coupling your standard model with the gauge body directly?
Like have the standard model particles carry some dark U1 charge. So if the I think if you require the standard model particles to have like order 1 dark charges, then you'll need everything to be at a pretty high mass scale. So I mean that is like that is a possibility, but probably if you do it for light dark matter, the interaction rate will be too large. So I mean I will say that like a way you can recast this kind of mixing between the A prime and the standard model photon as saying that all the standard model particles that have electric charge also have like epsilonic dark charge. That's just a change of basis. It's the same description. So yeah, but if you really wanted to say, okay, no, the standard model particles have like charges of 1 or 2 or whatever under the dark gauge group, I suspect that in order to keep the dark matter sufficiently dark, you then need the dark gauge boson to be pretty heavy to express the interaction that way. Okay, so this is a case where if it is true that this is the dominant annihilation channel, then this just works like ordinary Dirac matter during freeze out, but at late times this factor that the chi2 is bulk, the abundance of the chi2 is very suppressed, suppresses the annihilation rate. And this is so when you look especially at accelerator and direct searches for like dark matter below the GeV scale, you will often see a line on that plot that says like pseudo Dirac fermion, thermal relic target. This is what it's talking about. It's saying that, and the reason it's not excluded by the CMB and by other bounds is because of this issue. And more generally, I've talked about here the case where dark matter annihilates against a partner as a way to get suppressed annihilation at late times. But of course, that doesn't have to be true. The general co-annihilation framework is the case where there is some partner particle that's involved in the annihilations with the dark matter, and you may need to take that into account in order to do the freeze out calculation. It does not always lead to essentially zero annihilation in the late universe. It can just modify freeze out more generally. But cases like this, where there's essentially only one main annihilation channel, or all the annihilation channels require the partner particle, and then the partner particle becomes very underabundant in the late universe, that can effectively evade indirect detection constraints. So like models like this are great if you want to do a nice, if you want to do a search in another channel, in a non-indirect detection channel, and you don't want to get ruled out by the CMB by similar constraints before that. But they're sad if you're someone who's working on indirect detection constraints and you want to see a big signal. These are generally hard to see. There was a question there.
Is this what people typically call inelastic dark matter?
This is also, yeah, so this is one of the ways to have inelastic dark matter. That was a question. Sorry, and just to repeat the question to people on Zoom, the question was just, is this what people call inelastic dark matter? This is one of the standard models for it. Question.
Why is that to annihilate A
standard model? Photons in the standard model?
The picture, so the question was why have I drawn this as like chi1, chi2 goes into A and then into the standard model. So the A here is off shell. So the picture, so in these, this is an example of a secluded dark sector where the dark matter is not charged under any of the standard model gauge bosons directly. And vice versa, the dark matter is not charged under the dark sector interactions, but there is this mixing between the gauge bosons. Although, as I said in response to another question, it is possible to like do a change of basis operation here, which recasts this mixing between the two gauge bosons as saying the gauge boson, which basically comes down to redefining what the dark gauge boson is versus what the photon is. And in that case, you can recast this as saying there's no mixing between the two. Like what we're going to call the gauge bosons are the eigenstates. But then all the standard model particles pick up an epsilonic dark charge.
Okay.
So, but yeah, you could add other direct couplings between the dark matter and the standard model particles, but in these secluded dark sector pictures, you typically assume that there's just that there's a limited number of portals between the dark sector and the standard model. Question.
And you also do the other way around, like diagonalizing and mixing such that the dark sector is nearly charged and the U1 and the
If the dark U1 is unbroken and so the dark gauge boson is massless, then you can do that. If the dark gauge boson has like a substantial mass, then that is a physical distinction between what we call the photon, which is massless, and what we call the dark gauge boson. So like, I mean, in that case, you usually just say, okay, whatever is massless, that is what we're calling the photon. If they're both massless, then, or both like very close to massless, then you can define things in multiple ways. Like you can say, okay, I'm going to define the photon such that the standard model particles have only photon charge and no dark charge. And then if you do that, what this mixing will turn into is, so then the dark matter has no charge. So yeah, there are multiple different ways to write this depending on whether you want to work with like the gauge eigenstates or the mass eigenstates. But if the mass eigenstates are degenerate, then it's the sort of only obvious separation is the gauge eigenstates. Okay. So that's one category of possibilities for how you suppress annihilation at like times, how you can make an indirect detection signal small. Is that something is required that that just is not present in the late universe. So another possibility is you have all the particles you need to annihilate, but the annihilation cross-section itself is suppressed. So if we asked, what sort of conditions of the late universe are there such that the annihilation cross-section could be suppressed then and not at early times? This could be the annihilation cross-section is suppressed at low velocities because the typical velocity of the dark matter particles will be much smaller at late times than it is at freeze out. Freeze out occurs when the temperature is about a factor of 20 below the dark matter mass, which means that V is only like 1/3. V squared is about 1/10. V squared over 2 is about 1/20. So if the annihilation cross-section is suppressed at low velocities, that will do it. Or if it's suppressed at low densities, or there are various, these are the two main criteria that are typically used. So the classic example of the first case is where the annihilation is dominantly P wave, and we talked about this a little bit last time. I'll take this question.
Wouldn't suppression at low densities just be the same thing as like the dark matter particles not being able to find each other? They're not being enough.
Yeah, effectively. So what I guess I mean is if you have an extra suppression at low densities beyond what we have already, beyond what is usually assumed for like the two body case. So for example, if I've got a three body, if I'm relying on a three body interaction or similar, there'll be an extra density scaling that comes into the picture. Or you can have there are some more exotic models where the particle physics of the problem depends explicitly on the background. And so then you might also be in that category. But yeah, suppressing at low velocities is more common as there are multiple fairly straightforward ways to do that. So perhaps the most straightforward is to say that the annihilation is dominated by P wave annihilation, there's no S wave component. So if we talk about the annihilation of non-relativistic particles through a contact interaction. And we just do a quantum mechanical calculation, or I mean, even a classical calculation, honestly. If we assume that the interaction is a contact interaction, then we can perform a partial wave expansion on the incoming non-relativistic particles, and we can write, and we can do an expansion in velocity of the annihilation cross-section that looks like that if that the contribution from a given partial wave corresponding to orbital angular momentum quantum number L goes as VRL to the 2L. So this is the orbital angular momentum quantum number for the two-body state. And you can think of this heuristically as if the particles have more angular momentum relative to each other, that's like they have a larger impact parameter, and that means that they go past each other at a large distance. And you can just do like a classical scattering or classical annihilation calculation and show that you get this VRL to the 2L scaling out of that, which I'm not going to go through in detail. But so what that tells us, so the assumption that I was making last time when I said, okay, let's assume that sigma v is constant with respect to velocity, that was equivalent to assuming that it's the L equals 0 mode that dominates. Okay, so L equals 0. So this is what we call S wave annihilation. Sigma VRL is constant. And this is a non-relativistic expansion. This will not work if you take VRL to C. This is the low velocity expansion. Okay. And so L equals, if on the other hand it's L equals 1 that is dominant, then we call that P wave. You can imagine a situation where L equals the dominant, where the leading order term in this expansion is L equals 2 or L equals 3, which would mean that like the L equals 0 and L equals 1 terms both have to be 0. So this P wave case generally only, this term will be the dominant term in the expansion at low velocities only if the L equals 0 term is 0 or very strongly suppressed. Okay. And so basically the case where this P wave term is dominant is usually because there's some selection rule that forbids the L equals 0 annihilation. So this is just like selection rules in quantum mechanics that say, when you do an atomic dipole excitation, you have to have like delta L equal, you have to have like delta L equals 1, delta S equals 0. It's just that kind of selection rule. So, a typical example, there are a couple of examples in the notes, but a typical example would be, so I'll give you one example. So let's consider the case where we have identical Majorana fermion DM particles that annihilates into real scalars. So the CP properties of the state of Majorana fermions annihilating here is that the two-body Majorana fermion state has CP has like CP of -1 times -1 to the L, where L is its orbital angular momentum quantum number. So if I ask, I have two Majorana fermions, something happens, two real scalars come out. So if I ask about the CP properties of this, for the properties of the two real scalars, it's just -1 to the L, where L is the angular momentum quantum number. But what you find out, so you ask, so this says to preserve CP, you need to change the total angular momentum quantum number when you go from the Majorana fermions to the scalars. So if CP is preserved, we need delta L equals 1 in this interaction, okay? Or delta L equals 3 or delta L equals 5, whatever. But we need delta L to be an odd number. Okay? But there's another selection rule in here which conflicts with that. The L equal for starting L equals 0. So suppose we look at S wave. If L equals 0 for the initial state, then, so if L equals 0, the initial state is made of two identical fermions. So what do we know about two identical fermions? Their state has to be antisymmetric overall. Okay. So, but if we're in L equals 0, that means their spatial state is symmetric. Like the wave function of L equals 0 state is just like this here. So L equals 0 means their spatial wave function is symmetric. So that means that their spin wave function needs to be antisymmetric. If I like when I flip the spins, I have to get an over or minus sign. So that means that the antisymmetric spin state of 2 spin-1/2 particles is the spin singlet. So yeah, so I should say, if this goes too fast, don't worry about it. This is, this is sort of just like going back to quantum mechanics, but if you don't have this immediately to mind at a dark matter school, that's totally okay. Feel free to read through. This is in the notes. Feel free to read through it later or come talk to me later. Because yeah, I'm not going to go into a huge amount of depth in this. So okay, so if L equals 0 for the initial state, then those Majorana fermions need to be in a spin singlet state, because in order to preserve overall antisymmetry. But we know, the final scalars don't have any spin. Like their only angular momentum is coming from their orbital angular momentum quantum number. So we've just said that for the initial state, if we have L equals 0 and S equals 0, our total angular momentum for the initial state has to be 0. But for our final state, so that angular momentum conservation tells us that J should be equal to 0 in the final state. J equals 0, S equals 0. But that unfortunately implies that my orbital angular momentum also has to be 0 in the final state. So that tells me that if L equals 0 for the initial state, I can't get delta L equals 1 in this interaction. So it would have to be CP violating. So if there's no CP violation in this theory, I can't stop. I can't, like, this annihilation will not happen with L equals 0. So if you work out the annihilation rate in detail, it's going to depend on some CP violating parameter. If your theory is CP invariant, then it'll be 0. Okay? So this is one example of a way to get a dominant P-wave signal. Yeah.
Are there people who think about this type of CP violation in relation to standard model CP violation and try to make them like?
There are definitely models where people. There are definitely models where people try to relate dark matter physics to standard model CP violation, most obviously in the case of axion dark matter and the strong CP problem. I do not feel like I have a good sense of the full literature on these models, but yeah, the classic example would be thinking about the presence of the axion giving you a CP violating a contribution to CP violation in the strong center. And I just want to give a reference. So that's one example of how you will naturally get P-wave annihilation just out of the symmetry of the theory. There is a nice review paper by Kumar and Mahpatia from 2013, which goes through like every matrix element you can possibly have and whether it's S-wave for P, whether it gives rise, every kind of interaction structure you can have, and whether it gives rise to S-wave or P-wave annihilation, and also whether it gives rise to suppressed or unsuppressed direct detection signals. So this is a useful reference, and it has more examples like this. Okay. So this is one very classic way to suppress indirect detection at late time. Now, if you have a velocity suppressed signal, that doesn't necessarily mean that things are hopeless. Marco has done some very nice work on, could you look for P-wave for indirect signals of P-wave annihilation at late times? But you do generally have to work with this V squared penalty of B in the present day is 10 to the minus 3. Your signal will be down by 10 to the minus 6 relative to the estimates that we did for S-wave annihilation. Okay? So it's not impossible, but it's not an exponential suppression or anything, but it does suppress the signal by quite a lot. So another possibility is that in this category is that maybe the suppression isn't based on a symmetry. Maybe there's some kind of kinematic suppression to the annihilation rate. So we could also have, and I think, did Josh talk last week about forbidden dark matter scenarios? Is that familiar? Yeah. So this is sort of a classic example of this case. You could have a case where the dark matter is actually annihilating something slightly heavier than it is. And that's fine in the early universe where the temperature of the dark matter is larger than the gap. But as the temperature of the dark matter becomes smaller than the gap, then the rate will get exponentially suppressed, not just power law suppressed with low velocities. So that's, since you've already talked about forbidden dark matter, I'll just put a note there. And there can be more mild versions of that kinematic suppression, like where the dark matter is annihilating to something just slightly lighter than it is. So then there's not a lot of phase space for that annihilation, and that can give you like an order B suppression instead of an order B squared suppression. Okay, so these are a range of ways to suppress dark matter annihilation at low velocities. And yeah, as we mentioned earlier, if annihilation could involve more than 2 particles, then that will give us an extra factor of the density, which is a strong suppression at late times. And of course, there's also the possibility, this is all starting from, we want the annihilation to be at a certain level in the early universe so that we can deplete the dark matter sufficiently. But the dark matter may never have been in thermal equilibrium with the standard model. If the dark matter is produced by freezing, or by some other similar mechanism, or by misalignment in the early universe, then it just may not have interactions that allow it to annihilate into standard model particles at all. Or those interactions may be extremely tiny. So these indirect detection signals are never a guarantee, but we can take models and ask, are they likely to have interesting indirect detection signals? Yeah, there was one other option that I wanted to mention. No, okay, I think I'll mention that in the next section. Okay, so that's this is broadly speaking how I would categorize the set of models that are really hard to see in indirect detection. So what about the other direction? What about enhanced signals? So my favorite example of an enhanced signal indirect detection is one that we've already talked about a bit, where you have some long-range attractive force between the particles, and that can lead to bound state formation, and it can just enhance the annihilation rate. So this is called Sommerfeld enhancement. And the basic idea is that if the dark matter is interacting through some force, which could be like the weak gauge boson, the standard model, or so could be some new force that is long range relative to the annihilation interaction and attractive, then that can enhance the annihilation rate dramatically for much the same way that if I have 2 oppositely charged particles, the fact that there's a Coulomb interaction between them makes them a lot more likely to interact. But this is a low velocity effect, because in order for it to be important, the kinetic energy of the particles has to be small compared to the potential energy. If the kinetic energy of the particles is huge compared to the potential energy, they'll just bypass each other. So this can also, so the same potential can also allow for bound state formation. So the basic parameter, yeah, question there?
Thanks. Is there anything general we can say about the gauge groups and like the couplings with this kind of thing?
So the question was, is there anything general we can say about the gauge groups and the couplings with this kind of thing? So it's certainly true that the simplest Sommerfeld enhancement picture usually, if it can be done for a U1 dark sector or for some like just scalar exchange between dark matter particles, then you just have a U power potential. But if you have a more general gauge group, you can still have a potential. You basically just need there to be some attractive channel for the interaction. So in a general gauge group, you'll have both attractive and repulsive channels. So there'll be like some combinations of there'll be some dark matter 2 body states that experience an attractive interaction and some that experience a repulsive interaction. In practice, what you do in this case is that you write down the Schrodinger equation with the appropriate potential, which is now some kind of matrix that relates the different dark matter states in the multiplet, and then you solve the Schrodinger equation with that potential. But in the limit where the gauge bosons are light, that potential reduces to just like a Coulomb potential times a matrix, and you can just diagonalize that matrix and pull out from that, what are the attractive channels and what are the repulsive channels. And then in the attractive channels, the result essentially just reverts to the Coulomb case. So yeah, in general, there's a range of gauge groups that can support something like this. You just need there to be one attractive channel. Does that answer the question? So I'm not going to go into a ton of depth in the Sommerfeld enhancement. Again, happy to talk about it to people who are interested. But the basic parametrics are for a Coulomb-like potential, so a massless force carrier. So we can say that we have the potential like V of R equals alpha D over R. Then we can exactly solve for the Sommerfeld enhancement. And so the Sommerfeld enhancement is the enhancement to annihilation from this long-range potential. And what we find is that, so this kicks in basically where the kinetic energy is less than the characteristic energy. So the Bohr energy of this potential is the coupling squared times the dark matter mass. So basically this kicks in for velocities less than the coupling. So this is my kinetic energy is less than potential energy criterion. So the Sommerfeld enhancement turns on at that point, and then once this criterion is satisfied, then the cross section just gets enhanced. Well, yeah, I guess I don't need the thermal average here. The cross section gets enhanced by a factor S, where that factor S is approximately given by 2 pi times alpha D divided by V rel. So it's a 1 over V scaling at low velocities, and that's for S wave. For higher partial waves, you get a scaling that looks like, the prefactor is a little more complicated, but you get a scaling that looks like this. So the Sommerfeld enhancement actually gets stronger for higher partial waves. Now, in reality, you don't usually have an infinite range potential. If you turn on an infinite range new force, then that's quite constrained, like the force limits. So in practice, usually we have something more like a Yukawa potential. So if instead we consider a Yukawa potential with mass Ma, so we'll call this mass Ma prime, then in this case, you get the Coulomb-like behavior. So if the force carrier has a mass, there will be a large enhancement, then a large enhancement is still possible, provided that the range of the potential, so 1 over Ma prime, is larger than the Bohr radius that you would get in the Coulomb case. So this is basically saying, provided that the range of the potential, the size of the bound state, does not get cut off by the finite mass of the A prime, then you can still get a large enhancement. So this is going to be R1 over alpha D M chi. So if that condition is satisfied, then whether the enhancement looks like the Coulomb case or not depends on the velocity. If the velocity is smaller than other way around. If the velocity is large compared to the ratio of the force carrier mass to the dark matter mass, then you can basically approximate this Coulomb potential. But once the velocity becomes small compared to that parameter, then the enhancement just saturates at a level that depends on Ma prime over M chi. So in this case, you get a 1 over V scaling down to some minimum velocity that's set by the mass of the force carrier, and then the enhancement flattens out. Question?
Yeah, just trying to think intuitively about this. I would expect there would be more enhancement for a lighter force carrier compared to the dark matter particle.
Yeah. So right. So if we think about if we were to plot S versus V rel. So in the Coulomb case, you know, you have like S is about 1 at high velocities, and then as you go down to low velocities, it takes on this linear scaling, right? So broadly speaking, what happens in the case with the force carrier is that it starts the same way at high velocities, it looks the same, but then it flattens out and saturates at some point that depends on MA prime over M chi. So if MA prime is really small, then you stay on this line for longer, and so you saturate at a higher value. Okay, so like, I mean, it is now. There's one subtlety here, which is that once you have a massive force carrier, you can also get resonances in the system, which occur when there's a bound state that has almost zero energy. And then in that case, you actually get a stronger scaling where it scales like 1 over v squared for a while until you saturate. And so yeah, and so then like it's not monotonic with the mass of the dark force carrier. If your dark force carrier is such that you happen to have a resonant bound state in the system, that will increase the rate by significantly more.
If we have a repulsive potential instead of an attractive one, we see a separation instead of an enhancement.
Yeah, great question. Yes, if you have a repulsive potential, you actually get an exponential suppression. Like it's not even just a V suppression. It's like e to the pi alpha d over the suppression. So repulsive potentials are very effective at turning off the annihilations. Yeah, so that's actually another way to get a suppression of late times. Question like that.
So in the master limit, if this relative velocity goes to 0, it seems that there's a divergence.
Yep.
Artificial or
No. No, yeah, if you think about the rate for Rutherford scattering, which is like interaction through a photon exchange, that goes like 1 over v to the 4. In reality, you're not going to have particles interacting with each other at exactly 0 velocity.
because we have streaming, because we have other potentials between all the particles, screens all the potential.
Yeah, but I mean also just because if I start out 2 particles at 0 velocity that are not interacting with each other, they're going to stay not interacting with each other. Right. I mean, but yeah, I mean that's real. So there is a limit on like how fast your cross section can diverge as you go to 0 velocity, which is the unitarity bound, which says that for each partial wave, you have for each individual partial wave, you have an upper limit on the contribution from that partial wave that goes like the contribution of sigma that goes like 1 over k squared. So when the non-relativistic limit, that's 1 over m squared v. That's 1 over m squared v squared. So that tells you that per partial wave, you can't get a scaling stronger than 1 over v squared in the cross section. But that's consistent with the sum-fold enhancement.
Unitarity bound is not violated by.
It's not violated by the 1 over v scaling. On the resonances, where as I said, you can get a 1 over v squared scaling in the enhancement, their unitarity does appear nominally to be violated. The way that gets regulated is that these like 1 over v estimates are actually 1 over v and 1 over v squared estimates are actually based on neglecting the they're based on calculating the effect of the potential on the wave function while ignoring the absorptive piece that corresponds to the annihilation. When you put in that absorptive piece correctly, it will regulate the result so that you don't violate unitarity, but you can still have a 1 over v scaling. I'm happy to talk with you more in detail about this. My collaborators and I wrote a paper on this in 2016.
Yeah, because I read this paper.
Yeah, okay.
Okay.
Yeah, so it's let me talk to you about this later because it will take time if we go into it in detail. Okay. So then in addition to the Sumfeld case I mentioned, I'll just say briefly, we can have bound state formation as another channel to enhance the annihilation rate. And we can also have temperature dependent resonant effects, which I think were mentioned briefly in the Gong show yesterday. You can have a situation. So these are all ways to put it. So temperature dependent resonance effects can either enhance or suppress the cross section at late times. Question?
Yeah, maybe a nice question. I was basically assuming that the interaction responsible for the annihilation is different from the interaction responsible for this attractive potential.
The question, right? So the question is, is the interaction responsible for the annihilation different from the interaction responsible for the potential? It can be, it doesn't have to be. So yeah, I mean, so like just I can give you a so a case where this comes up, just thinking about like weakly interacting dark matter particles, is where, so you know, I have the Wino. The Wino has a Chargino partner. I guess Jonathan Payne told you about supersymmetric dark matter. So like the classic Wino, you have the Wino, you have a Chargino partner, and it has an interaction with the W like this. Okay, so then the annihilation of these particles goes through this vertex, and it looks like this. Okay, so like that's the annihilation. But there is a potential for sufficiently heavy Winos that there is a potential that looks like this. Okay, so like if the W is sufficiently light relative to the dark matter, exchanges of the W it mediates a long range potential between Wino dark matter. So that's a case where like the processes are different. Like in this case, you're exchanging a W in the T channel, and in this case, you're exchanging a chi plus in the T channel, but it's exactly the same vertex. So you know, like that's a case where the vertex responsible for the annihilation is the same as the vertex responsible for the long range potential. But you could also have a situation where you know this long range potential is going on, but the dominant annihilation channel is for a totally different vertex. So it can happen either way. Yeah.
In the case of reversible potentials, how does it affect the annihilation, like through the large gravitational potential? My question is like, are there any bounds, like for interaction of order of electromagnetic scale or something?
So the question is, if you have a repulsive potential, like how would it affect like the distribution of dark matter in the universe?
Yeah,
Is
and
that
the
question?
annihilation
Like,
that signals that we get from large gravitational potentials, like neutron stars and stuff.
sorry, I'm not sure I total. So I mean, gravitational potentials are attractive. So
Yeah, but you could have like repulsive potentials. So there,
okay, I'll say a
bounds?
couple of things. So first, a repulsive potential exponentially suppresses annihilation. The second thing is a sufficiently strong repulsive potential can also affect how dark matter is distributed on the sky. So it can there are constraints on dark matter self interactions. The thing, however, is that in order to get a strong constraint on dark matter self interactions, usually you need an order 1 fraction of the dark matter particles to interact in the dynamical time of the system. Like if only 10 to the minus 12 of the particles are interacting or whatever, like in our annihilation cases, you're just never going to be able to see it. So, so that means that you know, typically you need somewhat stronger interaction strengths to see an interesting self-interaction signal than to modify the annihilation signal. That's it. If you think about especially for light dark matter, like for this sort of dark matter in a dark sector that I talked about, if you're talking about like 100 MeV dark sectors with a repulsive potential and a moderately strong interaction within the dark sector, and just a small coupling with the standard model, that can absolutely have visible self-interaction signals in the distribution of dark matter. But for heavy Winos that have some repulsive channel, there's no visible self-interaction effect. It's just too small. Just not enough of the dark matter particles interact the whole time. Okay, good. So that's what I wanted to add. You guys asked a lot of questions, which is excellent, but I will be skipping a couple of examples as we go forward. Okay, so that's basically what I wanted to say about scenarios where the signals are enhanced or suppressed, the indirect detection. So now I want to move on and start thinking about, all right, in a realistic indirect detection search going beyond these cosmological bounds that we've talked for so far, what kind of signals are we going to look at? So where I want to begin there. So our basic observation here is we are going to see some number of particles. They're going to have some number of energies, and we're going to be able to detect where they come from on the sky. Now, the question of where they come from on the sky, sometimes that gives us information and sometimes it doesn't. For particles like neutrinos and photons that travel to us in straight lines, if we know where the particle came from, we can often reconstruct back to the point where it was originally produced, at least in 2 dimensions. We can't always tell how far away it came from. But for charged particles like electrons and positrons and protons and antiprotons and antideuterons, their directions of propagation will be scrambled by the magnetic field of the galaxy and then the solar system, which means that we usually can't trace them back to their origin point. So for those, usually most of the information that we have is in the energy spectrum that we observe. So I first want to start by talking in the rest of today's lecture about the different kinds of energy spectra that we can observe. And then in tomorrow's lecture, we'll go on to talking about directional information. Question?
Yeah, this is kind of a naive question, but why can't we just sort of map out the magnetic field and see where these particles are going to go?
Okay, so the question was, why can't we like map out the magnetic field and then like reconstruct where the particles came from in the first place? So I think there are two answers to this question. One is that mapping the galactic magnetic field is quite hard because we have one observation point. Like, you know, all our observations have to be done from the Earth, and we're trying to construct like a fairly complicated three-dimensional distribution. We do have observational data on the galactic magnetic field. You can look at how the magnetic field, like Faraday rotates light coming from stars throughout the galaxy, and that gives you some constraints on the B field. And you can look at what we'll talk about later, as high energy electrons pass through a magnetic field, they produce synchrotron radiation. So if you think you know the electron spectrum, you can figure out information about the magnetic field from that. But the problem again is we've only got one point at which we can measure the electron spectrum as well. So there's, yeah, I mean, the basic problem is that there are a lot more unknowns than there are, when we can only do the measurement at one point in the galaxy. Like if we could sprinkle probes throughout the galaxy, then, you know, this would be a lot easier, but we have one observation point, and so there are a lot of unknowns and not really enough equations to let us solve them. So that's part of the issue. But the other part of the issue is just like how accurately can we measure the direction that things came in with. So I can give you an example. So we're going to talk later about an excess of high energy positrons seen by the AMSO2 experiment. And the leading explanations for this for a long time have been maybe it's coming from relatively nearby pulsars, or maybe it's coming from some exotic source like dark matter. So you might say, okay, but if it's coming from a nearby pulsar, you know, we're talking about things that are relatively close to us. We're talking about one source. You know, surely in this case, we should be able to tell the difference between that and an isotropic signal. It turns out that the magnetic fields are good enough at scrambling the particles that by the time, so this is like from the closest source of high energy cosmic rays to us, it's about 200 parsecs away. And you can ask, okay, if 100% of your positrons were coming from that location, what kind of anisotropy would you expect to see in the positrons by the time they reach the Earth? And it's below 1%. And the instruments that we have are not actually accurate to be, and like we cannot actually measure a 1% anisotropy, like sub 1% anisotropy at this point. But I mean, these experiments are all looking for anisotropies. They have upper bounds on it. The upper bounds are at the level of like a couple of percent last time I checked. So that's like also the issue, just do we have enough statistics and do we have a good enough directional reconstruction to be able to tell? And so that I think is also currently a limiting factor. So yeah, so it's but these definitely are searches you can do, like try to look for anisotropy and try to use that to figure out where these charged particles are coming from. And for higher energy cosmic rays, which travel, you know, but for higher energy cosmic rays, this is actually being, you know, productive in trying to figure out where some high energy cosmic ray hotspots are coming from. But it's just a hard problem. It's much easier for photons and neutrinos. Okay. But yeah, so that was a good question. So before we dig into these propagation details, let's just kind of think about what standard model particles could be produced by annihilation and decay, and what kind of energy spectra we might expect to see as a consequence. So let's just think about, okay, I'm a theorist, I have a dark matter model, I want to predict what kind of signal I would see in a direct detection experiment. So typically, step one in computing what that signal will be is I will, you know, write down my dark matter model, I'll write down my Lagrangian, I'll write down the rates to produce various standard model particles. But then if I'm looking for an astrophysical or cosmological signal, I want to know how those particles decay into stable standard model particles. So step one in translating a model to a prediction for observation. We'll take out DM physics. will predict some rate of SM particles produced, but then we need to know from that what the rate and spectrum of stable SM particles is. Because we're talking about astrophysical timescales here. The vast majority of the particles in the standard model are unstable, and their decay lifetimes are the decay lifetimes of particle physics. So almost always these particles will decay before they can get to us enough. So what we're going to see, suppose I annihilate and I make W bosons, like in this we know case. I'm not going to see the W bosons at all. And the W boson is not going to decay in my detector at all. What I'm going to see is the electrons, or photons, or protons, or antiprotons that came from the decay of that W boson. So this step, fortunately, we know how to do because it's standard model physics. It's, these are processes that we observe in colliders all the time. So this step is typically done with Pythia or Herwig or other event generators. And there's a nice tabulation of results for a lot of dark matter particles called PPPC for DMID, which is the poor particle physicist cookbook for indirect detection, which for dark matter indirect detection, of which Marco is one of the authors. So if you need to do an indirect detection analysis, Googling PPPC for DMID is not a bad place to start. And in particular, they've already pre-calculated a lot of the figure in Herwig results. But you can also just redo it yourself using the event generator. So that step is figuring out when I inject W bosons or quarks, electrons, or taus or muons, whatever, how do they decay? And the output will be some spectrum of the stable standard model particles. So that's electrons, positrons, photons, neutrinos, antineutrinos, protons, antiprotons, and heavier nuclei and antinuclei. Okay, so this step is all particle physics, has nothing to do with astrophysics, but this is usually your initial step from looking at any indirect detection signal. So then we can ask the question of, all right, so if I think about, there's a classification that I like to do about what, given a standard model final state, what kind of spectrum of particles am I going to get out, and what kind of searches are going to be productive as a result of that. So let me tell you, so I generally classify standard model final states basically into 4 categories for indirect detection purposes. So category 1, which is where most possible standard model final states live, is that when the dark matter annihilation or decay happens, it produces quarks or gauge bosons or tau leptons. Basically anything that is not electrons, muons, or neutrinos, okay? and not direct photons. So why do I classify all of these things together? The reason why I classify all these things together is that gauge bosons and tau leptons have hadronic decays. So these are all processes that at the end of the day, what's going to happen is you make a lot of quarks, and then those quarks hadronize. This goes to quarks. This leads to hadronization, and hadronization leads to copious production of pions. Okay, so if you're making, is that a question? Okay, so if we make a lot of quarks, they hadronize, they're going to make the lightest hadronic states, which are pions. So we can have either both neutral pions and charged pions, and in general, both of these will be produced. As soon as you make charged pions, if you look up the decay path, if you look up the decay path of neutral pions decay to 2 photons 99% of the time. So for all these dark matter annihilation channels, this is the main place that your photon signal comes from. You make a lot of neutral pions, and neutral pions decay to photons. And so the branching ratio into photons finally is therefore usually, some like order 0.1 to 1 fraction. So it's through this channel that I say everything in this category 1 is going to produce copious continuum photons. So these are not going to be photons like at some fixed energy, because quarks come out with all sorts of energies. The hybridization splits the energy between the different pions, then pions decay to gammas. So this will generally give you some kind of broad spectrum of photons. So if I were to plot the number of photons, well, I can plot the number of photons as a function of energy, you know, and actually I'll plot this in power rather than number of photons. You know, schematically, what I'm going to get for my photon spectrum is like some broad bump. It has some general energy scale that's set by the mass of the original dark matter particles, but it's not going to be a spike. It's going to be some broad spectrum, and with a pretty large amplitude. Now, from the charged pions, if you ask how charged pions decay, they decay first to muons and antineutrinos, to muons and neutrinos or antineutrinos, and then the muons decay into more neutrinos and antineutrinos and electrons. So this channel makes neutrinos and antineutrinos and electrons and positrons. So, you know, so this means that we also have a copious neutrino signal and charged lepton signals. And if you've got enough center of mass energy, when you hadronize, you'll also make protons, you'll also make neutrons, you'll make heavier baryons that can decay down to other hadronic states. You may even make heavier nuclei and antinuclei like deuterons and antideuterons. So this is kind of so you'll sometimes see in papers, people show limits for indirect detection that are just like annihilation to B quarks. And you may have been like, why annihilation to B quarks? Like, why is this the only thing that we're showing? But part of the answer is that if you're annihilating into any one of these channels, the details of the channel often don't matter that much, because what's going to happen in all these cases is you make a lot of pions, and the pions make a broad continuum spectrum of photons, and copious neutrinos, and electrons and positrons, and it doesn't matter that much what state you went to initially. It matters in detail. Like, I mean, the shape of the spectrum will be different. You know, if you have a particular signal that you're looking at, then you may be able to figure out which final state you went through by looking at the detailed shape of the energy spectrum. But as first approximation for figuring out how strong your constraints are going to be, they're probably going to be fairly similar for all of these channels. Okay. Okay. When I say you at sufficient center of mass energy, you can produce heavier hadrons. So the stable states here, going up in mass, we have antiprotons and protons. We have antideuterons. And eventually, possibly anti-heavier nuclei. I will just note, and we may say, I'll say a little bit more about this later, that as we go to increasing mass here, the calculation of the production cross-section, like of how they're produced in these decays, also becomes increasingly uncertain. And yeah, I'll tell you about it. So AMS is actually AMS actually claims to see some anti-helium events, which is very surprising. This is going to say theoretically challenging, which is very surprising. From the perspective of these standard calculations. Even if you posit dark matter, we don't expect to make many anti-helium events by basically any mechanism that we know about. But there are big theoretical uncertainties in the estimated production rate for anti-helium. Okay, so that's basically category one. So category one, you make all types of particles, you don't have a lot of sharp features, but you can search for these in a wide range of ways. Okay, so what's category two? So category two is the leptons. So where we make, let's see this question there. Was there a question there? Yeah.
Can you see some normal matter? Like, can you discriminate between, like, for a signal for dark matter?
Excellent. Right. So yeah. So this I mentioned this briefly in the first lecture. So right. So for all of these channels, the reason why I'm making a point of, this is what the energy spectrum looks like, is that at the end of the day, if you see this signal, you're going to have to figure out, okay, is this a dark matter signal or is it coming from some kind of ordinary physics? You can win here somewhat, when looking at charged particles, you win here somewhat by looking at antimatter, not ordinary matter, just because there's a lot less antimatter in the universe than there is ordinary matter. But still, there are conventional mechanisms by which to produce high energy antimatter particles. If you go after these like antideuterons and antihelium channels, then we expect the background for that to be essentially zero. However, as mentioned, we may also expect the dark matter production rate to be essentially zero, and there are big theoretical uncertainties there. This, when I make the point that this is sort of like a broad bump, this spectrum of photons, if you have a spectral line, that's much easier to tell apart from ordinary matter. If you have a broad bump like this, it's much harder to tell apart. We actually have a giant signal of a continuum bump of photons coming from the galactic center. And the debate that's been going on for 10 years or so is, you know, are we looking at a potential dark matter signal, or are we looking at a bunch of photons from pulsars? So, yeah, so this is just a signal prediction. We're going to get to talking about extraction from the backgrounds later. But yes, these hadronic channels, because they tend to make these relatively smooth spectra, are often quite difficult to distinguish from the background unless you're producing very rare particles like antideuterons or antihelium. It's a good question. Okay, so second class of scenarios is where we annihilate into light charged electrons, so electrons or muons. So if we make muons, then if we make electrons and positrons, we're done. They're stable. You know that those particles will propagate to our detectors. If we make muons, they'll decay into electrons and neutrinos. So these channels make lots of charged electrons, but not a lot of photons, because there's no production of pions or something else that's going to decay directly with photons. And you'll get neutrinos if you make muons, but not if you go to electrons. So if you want to get a photon signal out of these processes, you need to go beyond the basic two-body final state. You need to go beyond just like E plus E minus or mu plus mu minus. These are charged particles, so they can radiate photons in the interaction. But so that's a radiative effect, so the rate is generally down by a factor of alpha. So gamma's only from three-body states or secondaries. So by secondaries, I mean that as these charged particles propagate through the galaxy, they can emit photons as well, like after the original interaction point. And we'll talk more about that when we get to cosmic ray propagation. Question there?
Yeah. Are there observational groups that are like? I guess my question is like, are there charged electron telescopes? Is that a thing that exists?
Yep.
Okay.
Yeah, absolutely. So the AMSO2 experiment is sort of the flagship one. There are actually a number of experiments looking for charged electrons, like Dampi and Calat. Fermi have also all done measurements of the high energy electron spectrum. The thing that's nice about AMSO2 is it has a magnet, so it can tell the difference between positively and negatively charged particles, so it can separate out the positrons.
Yeah.
But yeah, so AMSO2 and before it, Camilla and other experiments have done measurements of the high energy cosmic ray spectrum, and they've told us a lot about cosmic rays in our galaxy, and there are a number of excesses in AMSO2 data that might be telling us something about dark matter, but may also be telling us just about the local pulsar population or about other backgrounds. So in this case, if we want to look at like the photon spectrum from production of these mechanisms, so now we have a small peak at high energies from three-body states. So when you have a three-body state, so a photon emitted off the electron, then you get an enhancement where the photon is like collinear with the electron. And what this tends to lead to is a relatively sharp peak at energies near the maximum. So if we've got just two dark matter particles annihilating, the kinematic maximum is like two particles come out and each have energy equal to the mass of the dark matter. If there's a photon that's radiated along with those electrons, you end up getting a relatively sharp spectral peak for that photon. So this is sometimes called the final state radiation peak near the endpoint. And then what you will often see is then a lower energy continuum of photons So this comes from secondary particles. So this is photons emitted as charged particles travel through the galaxy. So we can look direct. So in this case, we can look directly for the electrons and positrons, or for the neutrinos produced from the interaction. But from the photons, we have these two contributions, this prompt contribution coming directly from the interaction, and then this delayed contribution as the particles propagate through the galaxy. For the second one, we need to understand how those charged particles propagate. So that's an extra level of complication in the prediction. Question?
I might have missed this. What about, do you care about photons that come from like pairs of electrons annihilating?
Good question. So the question was, do we care about photons that come from pairs of electrons annihilating? Yeah, so if you, that's a very good point. So if you produce positrons in here, so we generally don't care about photons that come from the positron and the electron that came from the same annihilation, like finding each other and annihilating. That's very rare. But what's much more common is that if we produce positrons in these interactions, they can just hit an electron out of the galaxy and annihilate. And yeah, so there will be a contribution from that as well. There can be a 511 keV line here. And yeah, so that is another possible signature of electron positron injection. Good point. Okay, my time. Okay.
Uh-oh, we lost it.
Oh no. Oh no. Okay. Sorry. Let me just pop back into Zoom. Not sure why it kicked me off sharing, but you were kicked out of the Zoom, or
Yeah.
okay. I appear to be back. Can the people on Zoom still hear us?
Yes.
Okay.
Yes.
Okay, they say yes. Very, very good. Okay. So third category is if you have a situation where the dark matter annihilates directly to photons. Okay, so the dark matter, so direct annihilation decay to blind photons. So this is the dream signal from the perspective of an indirect detection specialist who doesn't want to have to deal with backgrounds. So the situation here is like two dark matter particles come in, two photons come out, each of them carrying half the energy of half the center of mass energy of the original interaction. Question?
Wouldn't it not be dark then?
Good question. Yes, the question was, well, wouldn't it not be dark then? So yeah, that's the catch. Usually, if this is going to happen, it has to have quite a suppressed rate, or it has to happen through a one loop interaction. So so usually this is expected. Right. So the nice thing about this is, spectral line at sufficiently high energy, there are no backgrounds to this. Now, if your dark matter is much lighter and the energy of the dark matter mass is like an X-ray photon instead of a gamma ray photon, then there are some backgrounds to this just from like atomic and nuclear transitions. But you go up to high enough energies, there are basically no backgrounds to this. Your photon spectrum that I've been sketching before looks like that. So, it's a nice distinctive signal, but expected to be small because the M is dark. So this is a very clean signal. You can set beautiful constraints on it, but when you see limits that say the bound on this is way below the thermal relic cross section, that doesn't usually tell you that like dark matter of that mass is ruled out as a thermal relic, because the expectation is only a small fraction of annihilations will be into a channel like this. Is a question for that?
Right, so what kind of models do we expect to execute this kind of signal?
Good question. So the question was, what kind of models do we expect to get that signal? So in general, you expect, so one way to get this signal is if you have some kind of heavier charged unstable particles in the spectrum of the dark sector, and so the dark matter can go through a loop with those charged particles, and that can radiate photons. So again, coming back to sort of the supersymmetric dark matter case that you talked about with Jonathan Feng last week, like I said previously, we know dark matter annihilates like this into W plus W minus, and that is indeed the dominant annihilation mode. But we could do a suppressed annihilation mode. like, let's say I could close, so like in this case, I could close the loop of W bosons around here and have 2 photons come out here, or I could instead have like chi naught radiated W here, have this be chi plus and chi minus, and then because this is a charged particle, it can go to photons. So okay, so like if I've got, I just need the dark matter to talk to something that is charged, and then which can be a standard model particle or a dark sector particle, and then I can make a loop that radiates off photons. There are other models, like, I mean, if the dark matter is nully charged, then it'll have direct annihilations into photons. They'll just be suppressed by the small nully charge of the dark matter, which usually needs to be a pretty small number to not be ruled out. But you just need to talk to something charged at some point. But yeah, usually this, so there was a claimed discovery, like a claimed signal back in 2012 of a gamma ray line from the center of the galaxy, and which had quite a big info cross section. And for that, you basically needed there to be charged particles, new charged particles in the spectrum of the theory that were just slightly heavier than the dark matter, so that you could do this kind of thing. Okay, so number 4 is dream signal. Yeah, question?
Is this different from like channels that you have on your own
Great question. So the question is this different from channels with only 1 photon in the final state? Right. So I wrote gamma here, but if it was gamma and some other particle, which each took away half the DM energy, then again you would get this kind of line signal. So that's a great point. Let's put a gamma X there. So this could be like a gamma and a neutrino, for example. Sterile neutrinos often decay like that, and it has all the advantages of the gamma line signal. Or when I wrote down these like results here, the rate is actually higher for gamma Z than gamma. If the dark matter is heavy enough, the Z is almost massless relative to the dark matter. They again just come out like back to back, each carrying half the dark matter, half the COM energy. So yeah, that's a great question. Okay, so the last category, which is hard to observe, is you only make neutrinos. This is pretty hard to see because while we have good neutrino telescopes at high energies, neutrinos just don't interact very well and they're hard to catch. So, and for low DM masses, these are just extremely difficult to observe. So at high DM masses, so by TeV plus dark matter masses, dark matter energies, then there's sensitivity from neutrino telescopes like Antares and IceCube. But this is just generally a difficult channel to constrain. When I show you this current status quo constraints, you'll see that if we annihilate directly the neutrinos, we basically can't test the thermorelic cross-section of any mass.
So I'm not sure what you mean by this last bit here, but for high dark matter masses, aren't some of these neutrino bands competitive even with like direct detection bands?
Yeah. Okay, good. So yeah, so I'm thinking about neutrino bounds on annihilation and decay here. There are also bounds where you look for if dark matter catches in the sun and then annihilates and decays into neutrinos. That sets a limit on the scattering. So that's usually thought of as setting a limit on the scattering cross section because that's what's responsible for capturing them in the sun in the first place. But yeah, that's right. I mean, so you suddenly can get interesting constraints on dark matter properties.
What if I can constrain the scattering cross section? Can't I just constrain the coupling and do the same thing for annihilation?
So I mean, it's model dependent, but like but yes, right. So this is good. So let me add a caveat here. Difficult to observe, although the rate can be enhanced if you have capture in the sun or some. I mean, this is true for a range of channels. If you've got a compact object nearby that can capture the dark matter and like increase its density dramatically, then that can give you an easier to see signal. So enhanced from solar capture.
So the thing that always kind of confused me about this is, I mean, we try to constrain dark matter from the neutrinos coming from the sun, but we know there's tons of standard model neutrinos coming from the sun. So how can we possibly disentangle the two?
You're not going to get TeV standard model neutrinos coming from the sun,
Sure.
I think. or not a lot.
Right.
So I mean, yeah, it's right. So I mean, I think the answer is the
Yeah.
energy spectrum is what lets you try to do the separation.
That's great.
But yeah, so just to clarify what I said when it's model dependent, so you can, so in this pic, and then yeah, I realize where I need to wrap up shortly, but that's fine. I'm nearly at the end of this section. So yeah, so in that case, we're constraining typically the spin-dependent scattering of dark matter particles, which allows them to be captured in the sun. And direct detection is constraining, both the spin-dependent and spin-independent scattering of dark matter particles. So then the question may be, okay, like suppose I measure the coupling and I say, all right, then what kind of annihilation signal should I expect? The reason this isn't very model dependent is because, as well as, we've just talked through how there can be these model dependencies that either enhance or suppress the signal in indirect detection very strongly. There are also model dependencies that can enhance or suppress the signal in direct detection very strongly. Like one of these is, is the cross-section spin dependent or spin independent? But another one is like, does the cross-section have a momentum dependence in it or not? Like does the interaction structure lead to a dependence on the transfer momentum squared something? And if you just have a pure scalar, if you just have like a scalar contact interaction where you just say, okay, we really can just sort of write down we really can sort of just do the naive thing where we say direct detection is this diagram, and then we rotate it by 90 degrees and then and get this diagram for annihilation, and you just assume that both of these are just described by, you just assume that both of these are described by some number. Above 10 GeV, it is usually true that direct detection is stronger, because direct detection is probing really tiny cross sections, that are well below thermal relative to simplest models. But when you look at actual models, there are many, many cases where the direct detection signal is quite suppressed. I mean, again, if I want to go back to this, go to an example of supersymmetric, we know dark matter, that's a case where it turns out the direct detection cross-section shows up first at one loop. Like there's just no tree level scattering. So, but there is tree level annihilation, and the tree level annihilation is actually Summerfeld enhanced. So in that case, the direct detection cross-section is like just above the neutrino floor for thermal we know dark matter. The indirect detection signal is like way above thermal and is already probably excluded by gamma ray and anti-proton observations. So yeah, at the end of the day, like that comparison between scattering and annihilation is pretty model dependent, and just doing the simple like rotation of the diagram can be pretty misleading. Okay, so I just want to mention two more things before we wrap. So the first is, in this neutrino case, if I'm making really high energy neutrinos, they can actually radiate double duality bosons. And so then you're back to scenario one, where I make gauge bosons and they decay and they make photons and they make charged leptons and stuff. So those signals can actually be easier to see than the primary neutrinos. High energies, radiation of WC is important. The second is, you will have noticed as I went through these four categories that I was only really talking about sort of two-body standard model final states. That's because, if these states are available, they tend to be the ones that have the highest rates. But sometimes they're not available. Sometimes you have to annihilate into a three-body or higher standard model final state. That, broadly speaking, generally just sort of smears out the spectrum a bit in energy and doesn't really qualitatively change these conclusions. There's also the possibility that, like, what if the annihilation or decay isn't straight to standard model particles? What if you go to some intermediate dark sector particles and then the dark sector particles decay to standard model particles? Again, the effect of that is usually just to like somewhat broaden the spectrum, because the energy gets divided between the dark matter particles in a non-obvious way, and then when they decay to standard model particles, the energy of the standard model particles depends on the depends on like the direction of the momentum vectors of the standard model particles. There's an example worked out in the lecture notes if you want to go through it, but broadly speaking, the effect is usually just to broaden the spectrum somewhat. And there's my collaborators and I wrote a paper on this a few years ago, and other people have also written papers But if you want to read more about these dark sector cascades, then one place to start is Eller et al. So this is actually like this broadening effect is most striking when you have a case like this gamma situation where the baseline spectrum is very sharp and then going through some intermediate dark sector states can spread out this like sharp delta function into the box spectrum. It's also possible that you annihilate two dark sector particles that don't decay back to the standard model, or that only decay back to the standard model after a very long path length. If it's the latter case, so like a very displaced decay, so a displaced decay on the scale of the galaxy, then that will change the spatial distribution of your apparent signal. So we'll talk a bit more about the directionality of signals tomorrow. If the invisible particles just don't decay at all, then they could constitute like some dark radiation component. They could, or some dark matter component if they're not relativistic. And so then we have to come up with astrophysical and cosmological searches for that dark component, but you won't see something in indirect detection in that case. Yeah. So that's basically the spectrum of kinds of signals that we can see. Okay, so I want to wrap there for today. So tomorrow we'll return and I'll talk a bit more. I've said a little bit about these secondary particles that could be produced as charged particles propagate through the galaxy. So we're going to start tomorrow by talking about how charged particles propagate through the galaxy. And how that propagation modifies their spectra and the secondary particles that are produced along the way. And we'll also talk a bit about astrophysical backgrounds in that context. And then, so looking at the timing so far, then I expect tomorrow we'll then talk about J factors, about directional signals, but probably the discussion of the current status of the field will start in lecture 4, not lecture 3. So we'll start that on Thursday and go through that. Okay. Thanks very much.